In fact, the last topic in virtual memory is thrashing, which is a topic that we have introduced last time. So since we have introduced it last time, so let me ask you, what's thrashing?
A process is doing more time doing switching than it is actually executing.
Switching of what?
Switching of pages.
It's in fact loading of pages.
Loading.
Or it's spending, a process is spending most of its time waiting for the system to service a page fault. The system services a page fault by loading pages into memory and unloading sometimes copying in both directions. So that's thrashing. Now, what was the example that we used last time? Last time we used an example to show thrashing, how thrashing happens and why.
An array.
So we used an array. We used an array with 4 pages. Array with 4 pages, and the system is, or a program is doing sequential access of this array. Okay, so in this example, when does thrashing occur?
Every single time you try to...
Under what condition will thrashing occur?
When you load a page that's not actually there. So,
No, that's a page fault.
When it's
So,
full.
what do you mean?
When there are no more frames available.
No more frames available. Okay, yes.
When there are less frames allocated, then
There are pages.
Yeah.
So when the number of frames allocated to this process is less than the number of pages, like in this example we have 4. If we have less than 4 frames, if we have 3 frames, we will get lots of page faults. And of course it depends on the page replacement policy. So last time we showed that with 3 frames and with the least recently used page replacement policy, what percentage of the page accesses will result in page faults?
100%.
100% of the page accesses, remember, but not 100% of the memory accesses, because each page will still have multiple data elements in it. All right, so if if each page say has 1,000 integers in it, then the page fault rate is going to be in fact 1 over 1,000. If each page has 1,000 numbers in it. So, but what percentage of page references will result in page faults? It's going to be 100%. While if we simply increase the number of frames from 3 to 4, with 4 frames, what percentage of page accesses will result in page faults?
only the first 4%. Like only
The first 4, so
Yeah, only the first 4 page accesses out of 4,000 page accesses. So it's going to be 1 in 1,000. So only the first iteration. Only in the first iteration there will be a page fault. After the first iteration, we will always find the page in physical memory. So the point here is that a small increase in the number of frames can result in a huge decrease in the page fault rate. Or in other words, the flip side of this is that reducing the number of frames by only 1 in this case resulted in a huge increase in the page fault rate.
why is it 4 out of 4,000 instead of 4 out of 1,000?
Because there are 4,000 page accesses in this loop. Each iteration will access 4 pages. How many pages does each iteration access? Each iteration accesses 4 pages, and there are 1,000 iterations. So there's a total of 4,000 page accesses for the whole loop.
Divide 4,000. The
Okay.
percentage.
All right, so this is the idea of, now, thrashing means that you don't have enough frames, and the page fault rate is high, and the process spends most of its time waiting for the system to service page faults. But if multiple processes in the system are thrashing, then there will be a competition for the I/O device, for the disk. Most processes will be waiting in the waiting queue for the disk if you have multiple processes that are thrashing. If you remember in the earlier lectures, we talked about CPU-bound processes and I/O-bound processes, and we said that for good performance, we have to have a good balance between CPU-bound processes and I/O-bound processes, or in other words, we need a good mix, to have a good mix of CPU-bound and I/O-bound in order to have good performance. Now, when most processes are thrashing, what will happen to this mix of CPU-bound and I/O-bound processes?
More I/O bound?
Yeah, a thrashing process becomes an I/O-bound process. A thrashing process becomes an I/O-bound process because if it's thrashing, then the bottleneck is disk access. It will be spending a lot of time loading pages. Okay. So if all processes are thrashing, then basically we have, all processes in the system have become I/O-bound. Okay, and clearly, if all processes are I/O-bound, the CPU will be underutilized. The ready queue will be empty most of the time because processes will be spending most of their time in the waiting state, waiting for the disk. And the ready queue will be empty most of the time. Okay, now this is a very good curve that shows the relation between the degree of multi-programming and CPU utilization. By the degree of multi-programming, we mean the number of processes that are active in the system, that are loaded. Okay, so this is increasing the number of processes, increases CPU utilization, then until we get to a certain peak, then the CPU utilization will drop. Now, who can explain this? How does this relate to thrashing and to what we have just explained? Yeah.
Does it have to do with frame allocation and the fact that as we increase the number of processes and due to us having a finite amount of frames to allocate, each process would get less and less. And so at some point, we're going to have processes that run into situations like those where they spend more time swapping frames to and from disk, and because of that, it becomes I/O bound, and we have less CPU utilization.
Yes, exactly. So when we get to the thrashing point, when most processes are thrashing, we are no longer utilizing the CPU because the processes will be spending most of their time in the waiting state, and the ready queue will be empty most of the time. But before we get to thrashing, as long as we have enough frames, increasing processes will increase CPU utilization, because increasing processes will give the CPU scheduler more options. So when processes are waiting for I/O, the CPU scheduler will find other processes to give the CPU to. Okay. All right. Demand paging. So we talked about demand paging, and we talked about the concept of locality. We said that when a program executes, it moves from one locality to another. In this case, this loop is an example of a locality. What does it mean? It means that for a certain period of time, the program will be stuck in this loop, executing this loop many, many times, 1,000 times or many, many times. And when the program is executing this loop, there is a limited number of pages that it's accessing. So in this case, it only needs to access these 4 pages of data. And of course, it will probably be accessing a page of code, because there is code for the loop. So maybe 1 page of code plus 4 pages of data. And that's all what the program needs while it's executing this loop. This is the locality. Or we can, a different term is the working set. When the program is executing this loop, these 4 pages are the working set of the program. The working set is these 4 pages of data plus maybe 1 page of code. Now, when the program completes this loop, it will go into another piece of code, and then it will go into a different locality. So it may go into a different loop that accesses maybe array B. If it goes into a different loop that accesses array B, then it will be in a different locality, accessing a different set of pages and having a different working set. And this working set may be larger or smaller than this working set, depending on the size of array B. If array B is larger than array A, then this is a larger working set. If it's smaller, then this is a smaller working set. But also, working sets may overlap. So maybe this loop is accessing both B and A. So if this loop is accessing both B and A, then this working set overlaps with this working set. So A, the pages of A are common. Or maybe this loop is accessing only a subset of the pages for A. So different working sets are not necessarily distinct. They may overlap. But the point is that a program, as it executes, it moves from one locality to another. And what we want, from memory management point of view, is to have different frames, to have a sufficient number of frames for the number of pages that the program is currently accessing, or for the working set of that program. So that's why, one approach to thrashing, to resolving the problem of thrashing, is to try to estimate the size of the working set of each program. So if the system tries to estimate, the system comes up with an estimate of the working set of each program, and it does that for all programs, then it knows that the number of frames that are needed should be greater than or equal to the sum of the sizes of the different working sets. So the sum of the sizes of the different working sets for the different processes, that should be less than or equal to the number of frames that are available. Or the number of, if the number of frames that are available, M, is less than the sum of the working set sizes, then we know that we have thrashing. Some processes will be thrashing. Okay. Now, how does the system, how can the system estimate the size of the working set? It can look into a window of the last, n page accesses. What are the last n pages that a program accessed? And in this example, n is 10. It will look at a window of 10. What are the last 10 pages that this program accessed? So if we look at the last 10 pages for this program at this point, it has accessed pages 1, 2, 5, 6, and 7. Because it accessed page 7 4 times and page 5 twice. So this is the working set at this point. If we look at the working set at this point, at this window of 10, we will get a different set of pages. And the different set of pages here is 3 and 4, because here the program is only accessing 2 pages. Okay, so if if we estimate the number of pages or the size of the working set, the system should have a sufficient number of frames to accommodate all of these working sets. And if it doesn't, then sub-processes will be thrashing. And if the system detects that there is thrashing, then it will just suspend some processes. A solution to this is suspending some processes so that active processes have enough frames to run, or active processes are not thrashing. So this is the working set model. Another approach, yeah.
Is it feasible to completely eliminate thrashing?
Is it feasible to what?
Completely eliminate thrashing? Or are you trying to minimize it because you got to balance it?
Yeah, you try to minimize it. It's like, in the real world, it's, there are no perfect solutions. So you try to minimize it. And we will see in a little bit how an actual operating system, which is Windows, what it does in order to minimize crashing. The system tried to minimize it, but there is no perfect solution. A more direct approach is the page fault frequency approach, where the system tries to detect the page fault frequency, which is easy to detect. The system knows, the operating system knows, how many memory accesses a process has made, and it knows how many of these accesses resulted in a page fault. So it can just count. The system can count how many memory accesses, and it can count how many page faults, and then it can calculate the page fault rate. And if the page fault rate is too high, then that indicates to the system that this process needs more frames. And if more frames are available, the system is going to give it more frames. But the system can also detect that the page fault rate of a process is too low. And if the page fault rate of a process is too low, this indicates that this process probably has too many frames. So the system may take frames from a process that has a very low page fault rate. Of course, it will take these pages or frames from a process so that it can give them to other processes. So it will try to balance the system. So this is the page fault frequency approach here.
So would it try to keep the page fault rate closer to the lower bound, so you could keep the minimum?
Well,
number?
within the acceptable range.
Well,
so
yeah.
it will try to keep it within, between the lower bound and the upper bound. So that the page fault rate, it tries to keep it within a certain range. If it goes below the lower bound, then the process probably has too many frames. So it will take some frames from the process. If it goes above the upper bound, then the process probably doesn't have enough frames, so it will take frames from that process. But, it will give frames to that process. But remember that everything is dynamic, so it's, things keep changing. So if, the system detects a high page fault rate here and gives the process some pages, that may not be enough because it may enter a different locality in which it will be using a lot more pages. So it's, the behavior of a process is dynamic. Okay, so this graph shows the relation, or it shows how the page fault rate of a process, speaking of dynamic behavior, it shows how the page fault rate of a process changes with time. It goes into peaks and valleys, and it peaks up, then it falls down, and the page fault rate drops to a negligible amount, then it goes up again. And why is that? So how is this consistent with what we have just explained? In other words, can anyone explain this curve? What does it mean?
Well, when the process moves on to another part in its process, it may have a different set of stuff that it needs to look at. So it might be trying to bring in a whole bunch of new pages at each iteration, or at a different part of that process.
Yeah, and when it's bringing new pages, the page fault rate is high. So for example, a simple example is, these two loops. This is a loop that accesses array A, and this is a loop that accesses array B. So when the program first enters this loop, the pages of array A are not in physical memory. So initially, like we said in the first iteration, there will be lots of page faults. So this is where the page fault rate starts going up in the first iteration. Then the page fault rate will go down, and then it will go to near zero if we have enough frames. It will go to near zero if we have enough frames for the processes. So this assumes that there is no thrashing. If we have enough frames, at some point we will get enough frames, and there will be virtually no page faults. Then, when the program, so this is, this flat section is what we will get when the program is in steady state executing this loop after loading all the pages. Then it will be done with this loop. Now it will start executing this loop. Now it will start loading the pages for array B, so the page fault rate will go up, then until it reaches a certain peak. Then once we have loaded all the pages for array B, the page fault rate will start going down until it reaches a near zero value. Of course, in real programs, it's not as simple as this, right? So this is an oversimplified example to show the concept. But in a real program, there will be things will be much more complicated. An array will not, a loop will not be accessing only a single array. Program will be accessing multiple pieces of data, and there will be conditionals. So there will be an if and an else, and there are certain memory locations that will be executed conditionally. So they will be executed in one iteration, but they will not be executed in a different iteration. So every iteration is different. Here, this is an oversimplified example where all iterations are the same. So just keep in mind, the reason why this curve looks like this, and this is not exactly zero, and this goes up and goes down, is because real programs have a much more complex behavior than we have in this very simple example. Okay. All right, so last thing we will talk about is the Windows operating system. So Windows implements demand paging with clustering. What does clustering mean? It means that when it fetches a page, or when it fetches a frame for a page fault, it will also fetch some of the surrounding pages. Now the question is this pure demand paging?
No.
No, so this is not pure. This is impure because it's fetching some neighbors. And here, what's the concept? What's the rationale behind fetching surrounding pages?
Locality.
Yeah, exactly. It's taken advantage of spatial locality, trying to capitalize on spatial locality, because the surrounding pages are the pages that are expected to be referenced in the near future. So if that guess is right, that will minimize the amount of page faults. So you will have pages preloaded before they are requested. On Windows, each process will be assigned a working set minimum and a working set maximum. And initially, the process will be given its working set minimum. But if it needs more frames, or the page fault rate for that process goes up, the system will give it more frames up to its working set maximum. And but at some point, if the system detects that the amount of free memory is too little, or it goes below a certain threshold, it will start taking frames back from processes. It will start doing what they call trimming. of trimming of the number of frames allocated to each process. So the system will take some of the frames back from processing, but the number of frames allocated to each process will never be below the minimum for that process. So this is how Windows tries to keep the system balanced and to utilize the frames and keep all processes running, trying to satisfy the memory needs of the different processes.
So it's never going to go below the min or the max, even if it's...
Yeah, so it will never go below the minimum and it will never go above the max. And then-
if there's like several page faults, even at the maximum is so unassigned, it'll just go through, just eventually get done.
Yeah, so it's so each process will have a maximum, but I'm not sure what the difference between the minimum and the maximum, or how big the difference between the minimum and the maximum is. I mean, it could be significant.